All right, let's talk about model evaluation for classification models. Now, whenever you have a model, you want to have some way of describing how well it works. We discussed this issue in linear regression when we were doing prediction. So let me give you a quick reminder of that discussion. We talked about when you have a predictive model, you have your original data and you split the data into training data and testing data. So the test portion is separate from the training portion. And when we did linear regression, we had metrics to describe the performance of the model. Mean absolute error, mean squared error, and chi-squared error. And you can see these all involved the difference between the predicted value and the actual value. Now, when we're doing classification, well, we have a different situation. We're not predicting values, we're predicting membership in a class. So we're going to want some kind of metric that depends on proportions, proportion of correct predictions, proportion of incorrect predictions, and so on. So we arrive at this question: what matrix do we use for classification as opposed to prediction? And in this video, we'll introduce these concepts. Now, all of these concepts are based on what's called the confusion matrix. So let me briefly introduce the confusion matrix. This is from Wikipedia. Now, when you see positive and negative, you can think class 1 and class 0. So that relates this table to what we've seen before. Now, before going into all of these terms, let's look at this specific example here. Suppose you have an experiment where you have 8 actual cancerous patients and 4 actual non-cancerous patients. Now, you may have some kind of test to determine cancer or non-cancer that you apply to these patients. And when you apply the test to these patients, of the actual cancerous patients, you correctly predict that 6 have cancer, and incorrectly predict that 2 of those do not have cancer. Of the non-cancerous patients, you incorrectly predict 1 has cancer and correctly predict that 3 do not have cancer. So you see there are 4 alternatives. This is true cancer, which is correctly predicted. This is true cancer that is incorrectly predicted. This is non-cancer, which is incorrectly predicted, and non-cancer, which is correctly predicted. So these 4 boxes indicate 4 alternatives. The 2 boxes on the diagonal are the correct predictions, and the 2 boxes off the diagonal are the incorrect predictions. Now, the terminology is introduced in this diagram here. Here's the same picture. So the actual positive that is correctly predicted is called true positive. Actual positive that is incorrectly predicted is called false negative. Actual negative that is incorrectly predicted, false positive. Actual negative that is correctly predicted as negative is true negative. Right? So all of these concepts, accurate, precision, and so on, are defined in terms of these 4 alternatives. And you can see the terminology gets somewhat intricate, but everything goes back to these 4 alternatives. So these numbers here relate to proportions in the different boxes. Now, accuracy is in fact the proportion of instances that are in the green boxes divided by the total. Precision is the proportion in this green box here divided by the total number of predicted positives. And recall is the number of instances in this green box here divided by the total number of actual positives. Now we'll be giving examples to make sense of these definitions. And we'll use our credit riskiness example. Remember, credit risk, we're deciding whether or not a person is a high credit risk depending on two different factors. So assume that we've trained a model for credit riskiness, and we want to evaluate that model on a test set, which is separate from the training set. Right, so accuracy is the most basic metric. It's the proportion of test samples for which the actual label matches the predicted label. So that's total correct over total test samples. Related to the confusion matrix picture, it's the ones in the green boxes divided by the total. Now, you convert to a percentage by multiplying by 100. You can have accuracy as a fraction or as a percentage. Now let's move on to precision and recall. Now you might be wondering, why not just stick with accuracy? Why all these other measures? Well, problems come up when the classes are not balanced. I.e., for instance, they're in a case where there are many more ones than zeros. Here, this condition is referred to as skew classes. Same thing as unbalanced classes, where one class, you don't have many examples in your data set. For example, if you're trying to classify fraud, certainly most transactions will not be fraudulent. So there will be many, many fewer fraudulent cases than non-fraudulent. Also cancer. In the general population, there may be many fewer cancerous cases than non-cancerous cases. So the one class is much smaller percentage than the other classes. And usually the one class that is scarce is the one that we're interested in. So a classifier may be good at detecting negative cases but not positive cases. But it's the detection of positive cases that's important. So in this case, accuracy would not be a good reflection of the classifier performance. And I can give an extreme example of this. Suppose you have a population where only 1% is cancerous, and you simply predict everybody as non-cancerous. Well, if you predict everybody as non-cancerous, 99% of the time you'll be right, but your classifier is useless for what you're trying to do. You're trying to classify cancerous cases. So in this case, your accuracy is getting inflated because your classifier performs very well on the instances that you don't really care about. So you want a measure of your classifier that talks about the performance of the classifier on the cases that you really care about. Right, here's another example. In the credit riskiness data set, suppose we have a test set of 1,500 negative, non-risky examples and only 50 positive, risky examples. But it's the risky examples that we really want to identify correctly. Now, suppose the classifier correctly predicts 1,300 negative samples. 1,300 out of 1,500, that's not bad. But only 10 of the positive examples. So what's the accuracy? Well, the total number of correct determinations is 1,300 plus 10. The total number of instances is 1,500 plus 50. So you've actually correctly predicted 84.5%, but you've only really predicted 10 out of 50 or 20% of the risky cases, right? So this slide makes the point I made before, that we could simply predict everybody as non-risky, and you get lots of correct predictions, but you'd get 0% correct predictions on the positive examples. All right, 96.8% correct accuracy, but you're not accomplishing what you want to accomplish, which is identify the risky individuals. So here we get back to our 4 possibilities. Something that's actually positive can be predicted positive or can be predicted negative. Something that's actually negative can be predicted negative or predicted positive. So these 4 correspond to the 4 boxes of our confusion matrix. Right? The actual positive and actual negative correspond to the different rows of the table, and the predicted positive, predicted negative correspond to the different columns. Right? So we have the 4 different alternatives correspond to the 4 different boxes here. 1 and 3 are correct identifications. 2 and 4 are incorrect identifications. And we have that terminology I already introduced before. True positive, true negative, false negative, false positive. All right? Now it's useful to be able to work out some examples of confusion matrix. If you're given data, you should be able to fill in the confusion matrix based on the data. So for credit riskiness, for example, with 50 positive examples, 10 correctly predicted, that means that there's a 10 in this box here. But since there are 50 total positive examples, there's going to be 40 in this box here. On the other hand, 1,500 negative examples, 1,300 are correctly predicted. The correctly predicted box is down here in the lower right. But since we have 1,500 total examples, there need to be 200 in this box here. And you do the same thing for any set of data. The same way here, 15 positive, 7 correctly predicted. That means in the top right, there's a 7. 15 means there's 8 left over. 270 negative examples, 200 correctly predicted. But the 200 in the lower right means there's 70 left over for the lower left. Flip through this very quickly. Same principle for these other examples. Now you could just say, well, dig everywhere and you'll get them all, which is true. But what you want from the expert is, if the expert tells you to dig somewhere, then you have a good chance of reaching a diamond. That's the precision question, so that's this first question here. How reliable or trustworthy or precise are the classifier's predictions? So if the classifier tells us that it's a 1, can we be confident that it is in fact a 1? Now, this second question here concerning class 0, the precision focuses on one particular class and not on the other. So precision would address this first question, but not this second question. So another way of saying this is, of the cases where the classifier predicts as positive or predicts as a 1, what proportion are predicted correctly? How many of those really are 1s? So if we take our confusion matrix, we're looking at the ones that are truly 1 out of the total of predicted 1s. So we're focusing on the first column, and we want the proportion of the first box over the total in the first column. Right? Now, a different question is, is our classifier actually finding the positive cases? Are a lot of positive cases slipping through or not? And you can think of this as being important, say, in a situation where you have a disease like COVID that you're trying to identify. Now, you definitely want to identify all the positive COVID cases. Now, a lot of the cases that you identify as positive may not be actual positives, but you want to be sure to get all the positive cases. In the diamond hunting example, that would be the question of getting all of the diamonds and not whether you dig precisely in the places where there are diamonds. So a very different question. So this is recall. How many are you pulling in? So you can think about you're in a lake and you want to pull in fish. How many of the fish are you actually pulling in? Right. So how many of the actual positive cases can the classifier find? How sure can we be the classifier has found all the positive cases? How sure can we be that there aren't some undetected cases? These are all different ways of phrasing the same concern. So we can summarize this as saying it, of the cases that are actually positive, what proportion have been correctly identified as actually positive? So here we're looking at the actual positives. That would be the first row. Now the false negatives are the cases that have slipped through. So when we're looking at recall, we want the proportion of instances in the first row that are in the first box. So it's true positive over true positive plus false negative. Right? Okay. So let's see how precision and recall work on some of the cases we looked at before where accuracy was not a good measure. Okay. In this case where we had 1,500 negative examples and 50 positive, and it correctly predicted 1,300 negative, but only 10 of the positive. So we have our confusion matrix here. The precision is going to be the number in the top box divided by the first column. So in fact, we have precision of 5%. You can see we've predicted a lot of people are bad credit risks that actually aren't. So this has very poor precision. What about recall? Well, remember we're looking at the top row here. We're only getting 10 out of 50 actual of the actual bad credit risks. So both the precision and the recall are very bad in this case. And so these are good measures for picking up the poor performance of this classifier. Now in the extreme example where we simply predict everything as non-risky, we can fill in our confusion matrix, right? We actually predict everything as 0, and the precision in this case is undefined because we haven't predicted anything as actually positive. And the recall is 0. As I said, the accuracy here is high because it does well on the class that you don't care about, but it does terribly on the class that you do care about. So we can do the calculations also for this confusion matrix here. And let's interpret these numbers. This matrix comes from image detection. You're looking at images of cats and non-cats. So in this case, that if you determine that an image is a cat, it has a good chance of actually being a cat. But you're missing a lot of the cats. Okay. So that's tells us something about this classifier. All right, here we have a cancer detection case. You have the numbers here, 160 positive, 10 are incorrectly predicted, so that gives me the first row here. 1750 negative examples, 600 correctly predicted. And you can work out the accuracy, precision, and recall based on these numbers. So the idea here is that of the actual cancerous patients, you are correctly getting a lot of them. So that's good, you're getting a good recall. But on the other hand, you're incorrectly identifying as cancerous a lot of patients who are not cancerous. So you have these inflated numbers of predictions that's bringing down your precision. All right. So as it says down here, if you use this classifier, it's really not going to be very helpful because you're identifying too many people as possibly cancerous, so you're not, you're certainly not going to want to treat them all. So it's worth spending some time thinking about the implications of high precision and high recall, and how these are two very different questions. Of course, you want to get both high precision and high recall. So low recall means that you'll miss a lot of the positive cases, but the ones that you identify as positive are quite likely positive. A high recall, low precision means that you are pulling in all your fish, but you're also pulling in a lot of non-fish.